Welcome back to the class. Over the weekend, I need to thank the students for giving me feedbacks. So we're trying very hard to have this live streaming, but at the same time, we're recording everything. But to improve the live streaming quality, now we're using a real internet connection. So I think it will be better, more stable. And over the weekend, I also modified all the PowerPoints. So now they're in 16:9 ratio, so all the recordings are better. And then mentioned by the TA, my Blackboard writing style and all the characters are now bigger, as you can see. All right, so a quick recap to what I covered last class. Last time we talked about divergence. Divergence operates on a vector. Here I'm using yellow to denote a vector field. So when we perform the divergence on a vector field, we arrive at a scalar quantity. Divergence is to measure the net outward flux of that given vector field in a very small value. And then we derived the divergence theorem, which states if we have evaluated the divergence of over a very small value, but in fact we have a very big structure, if we integrate all the small values to arrive at the total three-dimensional structure, that evaluation, a three-dimensional value integration, would be equal to a closed surface integration of the vector field, or I should use A. Okay? Let me use A to express a generalized field. Over the closed surface. So the last time we talked about the significance of divergence theorem is we can skip or avoid having complication in calculation for a three-dimensional integration and downgrade it to a two-dimensional closed surface integration. It will be easier. And today, in the later part, I will use divergence theorem to show you how electric field intensities can be calculated. So this will be used later on today. Now, directly after divergence, we need to deal with curl. And usually curl is a concept most students cannot really understand. So I will use PowerPoints plus some drawing to help you understand it. It is more than math. It has its physical significance, right? But basically, before we start, as compared to divergence, curl also operates on a vector field, but the result is another vector. So this is in contrast to divergence. Divergence, you operate on a vector, you arrive at a scalar, but curl operates on a vector field, but again, you have a product of the vector field, right? So let's begin. Curl. Well, the wording curl is like most Western people, they have curly hair, like curl, something curly. So in Chinese, it's 全度, if you can read it. Okay, 全度. But those are not giving you straightforward physical sense. What I would like to do is to show you this movie. Do you know what that is? We live in Taiwan. We encounter this almost every summer, typhoons. So typhoons are essentially a curl-free, non-curl-free field that we encounter on our daily lives. Okay, I will come back to this movie later, but this is very eye-catching. Okay, so think of a typhoon as some kind of field giving you curl, right? And now you should be thinking about what type of field does not give you curl. Okay, so let's talk about the next formal definition. When we try to evaluate the curl of a vector field, essentially we are trying to calculate the net circulation of that field. What does net circulation stand for? For example, I have my vector field A. It is a function of space, of course. But if I decide I form a closed loop, just call it C, a closed loop. And I want to know if I start from a certain point on the loop, and then I'm trying to measure how much of that vector field is, well, pushing me along the distance. Okay, therefore I have my vector field making an inner dot product to
从1页或2页可以重复，因为刚收音有点问题。刚收音有问题，所以可能要重复一下。
Okay, so let me repeat. So basically, this is a movie showing you typhoon. Okay, and typhoon is some kind of field that really gives you curl. Alright, so we live every day in Taiwan. Every summer we encounter typhoons. So we should appreciate typhoons. So these are like circulating fields. So this is not some field you see every day. The field circulates. Okay? So by definition, when we evaluate curl of a vector field, we're trying to see how much of that field is really circulating. So the net circulation means I have my vector field, a function of space, and if I form a closed loop, and somehow I walk on a closed loop, I start from any given point, and I want to know how much of that field is really trying to push me, right? Doing work on me. So the proper mathematical formulation is the vector field making an inner dot product with my differential length. So imagine this A is force. This is something you learned in high school, right? F dot dl is work. So this is really asking, if I sit on point P and the vector field is pushing me, okay? Pushing me in the direction of dl along the closed contour, then it's giving me work. So I'm gaining energy. But the question is, if I walk along the closed loop, the wording closed loop means you start from a given point, you end up at the same point. Right? So a closed loop guarantees you start from point P, you walk along this path, but again you come back and you end up at the same point where you started. And now you have to ask yourselves, after this closed loop integration of your given vector field, and you integrate along all the differential length, is that 0 or non-zero? In the daily life, in the world that we live in, usually gravity gives you some kind of force, right? So if you walk from the 2nd floor, like where we are, up to the 8th floor and come back, do you gain any potential? No. So in that case, if your Vector field is so-called conserved field, like gravity. The integration over a closed loop will give you a 0. So there's no net circulation. But let's come back to the movie as I promised. Typhoon is rotating, right? It's circulating. So imagine you throw yourself or your pet into the typhoon. What is the typhoon field going to do with you or your pet? It will speed you up, right? Initially, your pet or you is stationary, not moving. Once you throw it into the typhoon field, you start to accelerate. Why? Because the typhoon is itself circulating. So that means there are some type of vector field which is rotating, circulating, so that you start from this point, and as you progress, as you walk along this closed loop, you're gaining more and more energy. So even though when you come back to your initial starting point, your energy as compared to your starting point is more. So this is non-zero. Okay? So let's come back to the blackboard. Let me just draw you. Gravity, right? Gravity points towards the center of Earth. So it's unidirectional. If you walk in this path, a closed loop, you have segment 1, segment 2. For example, we're starting from second floor, where we are in Delta building. We walk all the way top up to the 8th floor, and then we come back. So over this closed loop, I started from this point, second floor. I took my stairs all the way to the 8th floor, and then I decided to come back. For this segment, I'm working against gravity. So my legs are working, right? So I gain potential, I gain height. But then as I walk down, I regain I lose my height. So eventually, in this case, if your field, your vector field is unidirectional, your net circulation will be 0. You don't gain anything by walking along this closed loop. But on the other hand, what happens if your field your vector field A now looks like that? That very much represents a typhoon, right? A circulating field. If your field is itself a closed loop-like distribution, then you walk for a closed loop. Along each segment, your vector field is giving you positive contribution. Each segment adds up. In this case, the first segment and the third segment cancels out. So you have a net 0 circulation. But in this case, each segment along the closed loop you're walking on, they all have the same sign of work donated from your vector field. So these are two different vector fields. One is unidirectional, another is rotational. So the physical meaning of performing curl operation in this movie. When we try to perform curl operation, in essence, we're trying to extract, are there any rotational contributions within that vector field. If we have rotational, so here I'm giving you a calculated vortex field, or like typhoon field. It is circulating, right? So just imagine you throw in a small particle, it will be accelerated and moves along how the field is rotating. And you're guaranteed to gain some kind of energy after one rotation. Per rotation, you're gaining some energy. And it is because this A dot dl, if A is everywhere in the same direction as your differential length, this O adds up. Nothing is being cancelled. So therefore, even though you walk along a closed loop, you start from one location, you come back to the same location, but eventually you gain in energy or height or potential. So you have a non-zero net circulation. So is that clear up to now? Are there any questions from the students online? All right. Okay, so the meaning is if we have a rotational or circulating vector field, it is a non-conserved field, 非保守场. Vortex field, typhoon, they are non-conserved because they're circulating, so your net circulation would not be zero. Okay? So in essence, the formal definition of curl operating on a vector field is you're trying to find the maximum circulation, net circulation, over a small surface area. For example, I have some vector field. I want to find the maximum amount of net circulation, so I want to know its direction as well as the magnitude. Right? After you perform a curl, you have a vector. So it has its direction, it has its magnitude. So I want to know along which closed loop would I arrive at the maximum amount of circulation or gaining in energy. Okay, so that's a definition. So if you perform the curl operation on the vector field, if that vector field has some component that is circulating, you can find it by performing this operation. On the other hand, if you have like gravity conserved field, 保守场, you don't have net circulation, right? So again, the definition is you're trying to find the maximum net circulation per unit area, and the direction gives you the sense of rotation. So we use the right-hand rule. For this case, we have a closed loop, so the direction of my circulation is given by the thumb, but it's actually telling me if you throw in the particle, it will be rotating, in this case, in a counterclockwise direction. 逆时钟 in this case. Okay? Use your right hand. Your four thumbs denote where the field is rotating, but again, this thumb is pointing in the direction normal to it. Right, so are we clear up to now? Okay, so take a look at the definition and try very hard to link to what I taught you in basic vector analysis. dl and delta s, what do they stand for? When you try to evaluate the net circulation, you're Vector field is making an inner dot product to the differential length. So this is telling you, whenever you choose a different orthogonal coordinate system to work with, you would have additional terms, right? Cartesian, the easiest. Spherical coordinate, the most difficult. But once you understand BL, you know everything. Okay, so later on, I will try to derive the expression for curl operation in Cartesian coordinate. Why? It's the easiest. And because you are smart, so I trust you. You can work on cylindrical and spherical coordinates. But again, you have this net circulation divided by differential surface. So again, there's no need to memorize anything. Once you understand how differential length, differential surface can be derived through your understanding, everything is based on definition. So curl operation is trying to find the maximum net circulation. You want to find its direction and you want to find its magnitude.